What we're going to do in this video is continue our discussion of the Kepler problem using geometric algebra. What I'd first like to do is review what we covered in the previous video. So if you haven't seen that already, please check that out. Then secondly, we're going to actually prove that the inverse square law produces conic sections as trajectories. Here's a summary of what we did in the previous video. We had two masses, m1 and m2. I then pick an arbitrary point over here. I then draw a displacement vector from that point to m1. Let me call that displacement vector r1. I do the same for m2 and call that displacement vector r2. And then I join these two vectors to form the relative displacement from m1 to m2. Let me call that vector r. We see from the vector sum that r is r2 minus r1. We then considered Newton's law of universal gravitation, and what we found was that the acceleration of this relative displacement vector r was equal to minus g times m1 plus m2 all over r squared. Remember this little r here, the scalar, is just the magnitude of this relative displacement vector times r hat. And remember r hat was a unit vector, a vector of length 1 in the same direction as r. And then I just defined up a constant called mu, which is equal to g times m1 plus m2. So let me write that. Mu is equal to g times m1 plus m2. This is what I called the gravitational parameter. That allowed us to write the formula r double dot is equal to minus mu over r squared times r hat. After deriving this equation, we started talking about some geometric algebra concepts. What we talked about was the bivector called h, which is the wedge product between the displacement vector r and r dot, the velocity. And remember, this was the angular momentum per unit mass. And very importantly, we found that this quantity is a conserved quantity. It's a conserved bivector, which I write as d dt of r wedge r dot is equal to 0, which is to say that this wedge product, this bivector, doesn't change over time. Another thing we did after we derived the conservation of angular momentum is we discovered the conservation of energy. And the mathematical expression that we derived for that was that d dt of 1/2 v squared minus mu over r is equal to 0, which is to say this quantity doesn't change over time. Notice here we have a conserved bivector quantity, and here we have a conserved scalar quantity. Also remember that we identified this first term, 1/2 v squared, as the kinetic energy per unit mass, and we identified this second term, minus mu over r, as the gravitational potential energy per unit mass. And one last detail that we covered, returning back to this angular momentum, was that we can write this r wedge r dot in a different way, which is r squared times r hat dot, where this product between these two vectors is the geometric product. So let's get right into the derivation. Here I have the acceleration equation, and here I have the angular momentum per unit mass equation. Now here's the piece of magic that I'm going to perform next. What I'm going to do is multiply these two equations together. I'm going to multiply h times r double dot. So I'm going to multiply this by this. And let's write that out. So on the left we have r squared times r hat dot. And then on the right we have minus mu over r squared times r hat. Now notice what happens. These r squareds here in the numerator and here in the denominator, those are both scalars, so I can swap those around, and I can swap the order around as I'd like. I'm going to cancel those out. And I see this minus mu here, that's also a scalar, so I'm going to yank that out to the front. So what I have is minus mu, and then I've got these three vectors here, but no, remember I've got to watch the order here in geometric algebra, so I'm going to write r hat dot, and then r hat, just preserving that order there. That's still equal to h times r double dot. Now, remember what we were saying in the previous video about this r hat and r hat dot. These vectors are orthogonal. Now remember that I'm allowed to commute those two under the geometric product as long as I flip signs. So that's exactly what I'm going to do. I'm going to commute these two vectors. I'm going to swap the order around. And that's going to flip the sign there. I'm going to get rid of that minus sign. So I'm going to have positive mu times r hat dot times r hat, and then times another copy of r hat. So I really have r hat squared here. And that's still equal to h times r double dot. Now, remember what a vector squared under geometric practice, that's equal to the squared magnitude of that vector. Remember, r hat was a unit vector. It's of length 1. So this r hat squared is simply 1. So I'm left with a very simple equation. H times r double dot is equal to mu times r hat dot. The next thing I'll do is rearrange this equation. I'm going to move this mu r hat dot to the left-hand side. So I have h r double dot minus mu r hat dot is equal to 0. Now remember that h is a constant quantity. It doesn't change over time. We showed that through the conservation of angular momentum. Mu is also a constant quantity. And what I'm going to do is integrate this expression. I'm going to notice that it can be written as ddt of the following. H times r dot, notice one dot only, minus mu times r hat. That's equal to 0. And make sure you convince yourself that going in reverse, this actually makes sense. And notice that we needed that property that h is a constant. So what is this equation saying? It's saying that over time, ddt of this vector quantity, notice that this is a vector quantity now, is equal to 0. So that's saying that this vector over time is conserved. So we've actually got yet another conservation law, that this vector, whatever it is, it's conserved over time. It doesn't change over time. Seeing as how this equation is telling me that this vector quantity is conserved, let me just yank that vector out. H times r dot minus mu times r hat, and set that equal to a constant. In this case, it's a constant vector, so let me call that C for constant vector. And I guess people who work in this field call this constant vector, this conserved vector quantity, the Laplace-Runge-Lenz vector. Actually, I think it's a scalar multiple of this vector, but like this vector here, it's a conserved vector quantity in this Kepler problem. So notice that we've actually done quite a bit in the abstract sense in this Kepler problem. We've got 3 conservation laws. We found that there was a conserved scalar quantity, a conserved grade 0 quantity called the energy. There's a conserved grade 1 quantity called the Laplace vector. Let's just call it the Laplace vector for now. And then we had a conserved bivector quantity, which was the angular momentum. So abstractly, we've got a lot going on here. And one other thing I'd like to do before we move on is remind you what this h times r dot is going to look like. Remember, h is a bivector, and r dot is just a vector. So what happens when you multiply the two? So let's say I had some mass. Let's say that's mass 2, which I'll represent by that point. Let me draw on the displacement vector r to that mass. Let's give the mass some velocity. So let's say r dot, the velocity vector, is going in that direction. There's r dot. So by wedging this vector and this vector, I form h. So let me draw in that wedge vector there, or that wedge product there. The orientation is going to be counterclockwise. So this whole thing, this signed area, this is the bivector h. And then notice that, or remember, when I multiply a bivector by a vector, that's going to rotate the vector 90 degrees and scale it. Now, if you check the orientation here, h times r dot is actually going to rotate this r dot vector 90 degrees clockwise. And it's going to scale it depending on what the area is here. So actually this h times r dot is going to look something like this. This is going to be 90 degrees, and that vector is going to be h r dot. So it swings this vector around 90 degrees counterclockwise, and it scales it depending on what the area is. So hopefully you can see that this thing is indeed a vector quantity, and I subtracted away another vector, which is mu times r hat. Remember, r hat is just the unit vector version of this vector, so r hat might look something like that. So hopefully you can see that this is indeed a vector quantity. Now, working with this Laplace vector is going to give us a really clean solution to the Kepler problem. So here's what we're going to do next. I'm going to move this minus mu times r hat to the right-hand side. So I have h times r dot is equal to c plus mu times r hat. And then here's another neat trick which I'm able to do because of geometric algebra. I'm going to multiply both sides on the right by the vector r. So on the left-hand side, I'm going to have h times r dot times r. Then on the right-hand side, I have c times r plus mu times r hat times r. Now here's what I'm going to do. I'm going to notice these two vectors here. Remember, the geometric product of the two vectors can also be written like this. R dot dotted with r. I take the dot product between those two vectors and add it to the wedge product between those two vectors. So r dot wedged with r. And we're going to do the same trick for the right-hand side. I'm going to dot these two vectors. So I have the dot product between that conserved vector and the displacement vector, plus the wedge product between the two. Then finally, I have mu times, I'm going to have the dot product between these two vectors, and then plus the wedge product. But notice that these two vectors are in the same direction, so I'm not even going to bother writing the wedge product because that's going to go to 0. So I'm going to be left with the dot product between these two. So r hat dotted with r. Let me now distribute the stuff on the left-hand side. So I have r dot dotted with r, that's scalar, times h. Notice that this quantity is a bivector quantity. It's just a scalar times a bivector. Here I have the wedge product between the velocity and the displacement. Now hopefully that sounds familiar. That's actually the reversed order of the way we define h. So this quantity here is actually the negation of h, because remember I can swap these two around as long as I stick a minus sign with the wedge product there. So this is actually going to distribute to minus h squared. And I'm going to show you in a second that this minus h squared is actually a scalar quantity. Then on the right hand side, I have yet another scalar quantity. So this dot product is going to be equal to the magnitude of c times the magnitude of r times the cosine of the angle between them. Now the magnitude of the vector c, I'm going to denote by plain old c. The magnitude of r, I'm going to denote by r, as I have been doing. Then I have the cosine of theta, and theta is going to be the angle between these two vectors, between the conserved vector and the displacement vector. Now I have this wedge product here. I'm going to just copy that down. I'm going to actually ignore it in a second. And then finally I have this last scalar value quantity. This is going to be plus mu. And then I do the dot product. It's going to be the magnitude of that vector, which is 1, times the magnitude of this vector, which is r, times the cosine of the angle between them. The angle between these two vectors is 0, so the cosine of 0 is just 1. So I'm left with mu times r, just another scalar quantity here. Next, let me actually show you that this minus h squared quantity is actually a scalar value quantity. Now, numerically, remember what h, this bivector, might look like. H could be something like minus 6 times e1, e2. Just some scalar multiple of the basis bivector e1, e2. And the scalar sitting out front is the amount of signed area that this bivector has. So this would be the signed area of the angular momentum. Now, what happens when you square this thing? So I have h squared is equal to the square of the scalar sitting out front, which happens to be 36, times e1, e2, all squared. Now remember what the basis bivector squared to. That squares to minus 1. That was that whole premise behind talking about the complex numbers. So this thing squares to minus 1, so I'm left with minus 36. So let me abstract this a little bit. Instead of saying minus 6 times e1, e2, let me say some scalar, little h, times e1, e2. And that's equal to big H. So you square this thing, and what you get is minus little h squared. And that minus sign, again, that comes from the basis bivector squaring to minus 1. So what I see is that minus big H squared is equal to the square of that scalar sitting out front. So that's indeed a scalar quantity. And actually, let me substitute that in right there. Minus H squared minus big H squared is equal to positive little h squared. Simply put, that's just the square of the angular momentum per unit mass. Now the next thing I'm going to do is I'm going to notice in this equation that I have both scalar and bivector quantities. I have a bivector, a scalar, a bivector, and the scalar. So what I'm going to do is on the left and right hand sides, I'm going to set the scalar parts equal to each other. So the only scalar part on the left hand side was at little h squared. And on the right hand side, I have two scalar terms. First, I have CR cosine theta. That's a bivector. And my other scalar quantity is that mu times r. Now that vector r, that displacement vector from mass 1 to mass 2, is really the vector I'm interested in this whole Kepler problem. So let me attempt to solve for r here on the right hand side. Now to do that, what I'm going to do is factor out the r. So I have r times the quantity c cosine theta plus mu. So to solve for r, all I need to do is divide by this factor here. So I can say that r is equal to h squared in the numerator divided by mu plus c cosine theta. And my last little trick is I'm going to divide both numerator and denominator by mu, because I want a 1 down there, as you'll shortly see why. So in the numerator, I now have h squared over mu divided by 1 plus c over mu times cosine theta. So this is where we're at so far. We've expressed r in terms of some constant in the numerator over 1 plus some other constant times cosine of theta, and now I'm going to treat theta as the variable. So I'm going to interpret this whole thing as a polar equation. It's an equation in polar coordinates. So r is going to be some function of theta. Now what I'm going to do next is I'm going to redefine some new constants. This thing sitting up here in the numerator, I'm going to call p, because everyone else does. P is equal to the square of the angular momentum per unit mass over the gravitational parameter. And the more important quantity, actually, this ratio of c to mu, I'm going to call it E, which is c over mu. This quantity here, the P, is a parameter of a conic section called the semilatus rectum. And this quantity down here is called the eccentricity. Now, of the two, the eccentricity is the one you've probably heard of. It's one of these famous parameters that characterizes precisely which conic section we're dealing with. And this is going to allow me to rewrite this equation in the form P over 1 plus E times cosine theta. And equations of this form, I claim, are conic sections. Let me show you that this equation actually is a conic section. What I'm going to do is cross multiply here and set that equal to P. So I have that R plus ER cosine theta is equal to P. Remember, now we're working in polar coordinates. Remember that this R cosine theta is equal to X. So on the left hand side I have R plus E times X is equal to P. And I remind you that this E is just a dimensionless number. It's just a plain old number called the eccentricity. What I'm going to do is I'm going to move this thing onto the right hand side. So I have R is equal to P minus EX. My next little trick is I'm going to square both sides. So I can say that R squared is equal to the square of P minus EX. Remember also in polar coordinates that R squared is equal to X squared plus Y squared. That's the left hand side. And the right hand side, I'm going to keep that around. P minus EX squared. And let me actually square that term. So the square there is going to be P squared minus 2 PEX plus E squared times X squared. That's still equal to that left hand side. And now my last little manipulation is I'm going to group all the similar terms together. Let me first group the X squared terms here. I've got one there and one over there. So I'm going to move this onto the left hand side. And that's going to give me 1 minus E squared times X squared. And now I'm going to keep that term which is quadratic in Y. That first term is quadratic in X. The second term is quadratic in Y. I now have this term which is linear, first degree, in x. Let me move that to the left-hand side as well. So I have plus 2pex. And then I'll just move that to the left-hand side too. Minus p squared is equal to 0. And all quadratic equations in two variables of this form are conic sections. Let's explore a few special cases of this polar equation. The first case I'd like to consider is the case when the eccentricity is equal to 0. Now what happens to this equation when e is equal to 0? We get a 0 in this term here. The denominator is just 1, so I get r is equal to p. So actually r doesn't depend upon theta at all. It's just equal to that constant p, which remember was the squared angular momentum per unit mass, divided by mu, the gravitational parameter. What does the plot of that look like? Well, the equation is saying for all values of theta, the radius should be p or h squared over mu, which is, of course, a circle. So all values of the radius independent of theta are equal to h squared over mu. So this is the idealized case where you have a circular orbit. Now these trajectories that we're drawing out here, these are the paths taken by mass 2 where you place mass 1 at the origin in this coordinate system. So mass 1 over time is going to be just at the origin. This is from mass 1's point of view. And these are the paths taken by mass 2. So we have the case where the eccentricity is the idealized value of 0, in which case we get the circular orbits. Now let's consider the case where the eccentricity is greater than 0, but less than 1. And this is actually a great deal of actual cases in the real world. Let's say the eccentricity is something like 0.02, which is the approximate eccentricity of the Earth's orbit around the Sun. So what kind of conic sections do such eccentricities produce? Well, I claim that these are the elliptical orbits. So this is the ellipse. And let's play around with this equation and try to graph this out. Ranging over possible values for theta. Let's let theta go to 0. So the radius that we're going to have to plot out is p over 1 plus e. So let me draw that out over there. So that x-coordinate should be p over 1 plus e. Then we let theta go to 90 degrees. The denominator just goes to 1 overall. And so we get the y value, also the radius, should be equal to p. Now I should also point out that the origin here, the location of mass 1, is going to serve as one of the two foci of this ellipse. And the distance from here to here, that p, that's precisely the thing that I was talking about called the semi-latus rectum. Now let's go to theta is equal to 180 degrees. So the value of the radius is going to actually be p over 1 minus e. But I'll introduce a minus sign because we're on the negative x-axis. So the x-coordinate is actually going to be minus p over 1 minus e. And then finally down here, we also get the other semi-latus rectum. This whole distance is called the latus rectum. So the semi-latus rectum is just half the distance from the focus to the point on the ellipse drawn vertically. So this y-coordinate down here is going to be, as you might expect, minus p. So we have 4 points here. These are all going to be 4 points on the ellipse. Here's one focus. The other focus might be over there. So the ellipse might be drawn out to look something like this. And that's your elliptical orbit. Now this trajectory that we've drawn out here just shows us the total trajectory of M2 when M1 is right at the center of that coordinate system. Now remember that we've already demonstrated the conservation of energy, also the conservation of angular momentum, or Kepler's second law. So as this M2 orbits around M1, it can't be going at the same velocity at all times as in the circular case. Now why is that? Because at some points it's further away from the sun, let's say the Earth is further away from the sun. That means the potential energy is changing. So to keep the total energy constant, the kinetic energy must also be changing. So at some points in the orbit, it must be speeding up. At some other points, it must be slowing down. If we take a look at this point over here, this minus p over 1 minus e, Notice that in this denominator, we've got a problem when e goes to 1, because we've got a division by 0 error. So let's consider how this elliptical shape starts to deform as we take e closer and closer to 1. Now, as e gets closer and closer to 1, this denominator gets closer and closer to 0, which means this whole thing blows up to negative infinity. So at this point, as I take e closer and closer to 1, it's going to start moving to the left, which means this whole shape starts to open up. And this point over here, this p over 1 minus e, when e goes to 1, this is just going to approach p over 2, which is a perfectly intelligible number. So we've got this shape which has a point over here. The focus is stationary. These 2 points are stationary. This thing blows up to minus infinity. Now this shape, when e goes to 1, is actually the parabolic case. Another way to see it, if you can't really imagine what's going on when you deform that ellipse, is to go back to that Cartesian equation with the x squareds and y squareds, plug in e is equal to 1, and you'll discover you get an equation for a parabola. You get an equation which is quadratic in y and linear in x, and that's an equation for a parabola. So this parabola is actually a pretty cool case, because in that case the particle has just enough energy to escape being a very, very wide elliptical orbit, or I should say a very eccentric elliptical orbit. It's just enough energy to not complete an orbit. So the last case to take care of is when the eccentricity is greater than 1. And I claim that these are the last possibilities for conic sections, which are the hyperbolas. So you can draw that out as an exercise. Try to convince yourself that this goes to a hyperbola. You can do it using the polar coordinates. You can go back to the Cartesian as we were working with before. So let's summarize what we were saying with those eccentricities. If you imagine drawing out a little number line for the value of e here. So at the value of 0 and the value of 1, we had some special exact cases. When the eccentricity is exactly 0, we had the circle. When we have something in between 0 and 1, we have the ellipse. When it's exactly 1, we have the parabola. And when it's greater than 1, we have the hyperbola. Now, there's a bunch more to say, and in the next video, I'd like to do a little analysis of the energy associated with each one of these cases. And what I claim is that these bounded orbits, the circle and the ellipse, have an energy which is negative, a total energy which is negative. In the case of the parabola, the energy is exactly 0. And in the hyperbolic case, where the thing doesn't orbit at all, the energy is positive. Now, we were talking about the Laplace vector before, just to solve the equation that we got for the Kepler problem, but I didn't say too much about what the vector actually looks like when we draw it on these orbital diagrams. Now, let's assume that we've got some m2 in an elliptical orbit around m1. Now, we know that this Laplace vector, no matter where m2 is on its orbit, has to be pointing in the same direction and have the same magnitude. It's a conserved vector during the motion of m2. Let's draw in a few vectors. Let's attempt to draw in h times r dot and also mu times r hat. Now, the vector r hat is going to be pointing from mass 1 to mass 2, so it's going to be pointing in that direction. And we just have a scalar multiple of r hat. So that means mu times r hat is going to look something like this. There's mu times r hat. Now, the velocity as m2 comes around like this is going to be exactly downward. Now, h times r dot, when that vector gets rotated 90 degrees clockwise, is going to look something like this. So notice we have two completely horizontal vectors being added together. So that means that the sum or the difference, whatever, of those two completely horizontal vectors is also going to be completely horizontal. So what that tells us is that this vector c is going to be also completely horizontal. And it's going to be completely horizontal at every point along the trajectory, because it's a conserved vector. If it's conserved here, it's going to be the same over here, over here, over here, and so on. The next question is it pointing to the left? Is it the 0 vector? Or is it pointing to the right? And to determine which of these cases it is, let's take another special point on the orbit where the velocity is pointing exactly leftward. Now, when you rotate that 90 degrees, what that means is that h times r dot is going to be pointing exactly upward. Now, r is going to be a vector from here to here. Same thing with r hat, it's going to point from here to here. Now what that means is that, actually let me draw that in there. Now I'm going to attempt to draw in mu times r hat, but remember that these two have to have a difference which is totally horizontal. So I'm going to draw it from there to there because I know that this vector has to end up being completely horizontal. So this vector minus this vector, if you just take a look at the vector difference, is going to point to the left actually. So this is the Laplace vector here that I've just drawn in C. So actually this is a vector which is going to point along the major axis of this ellipse, and it's going to point toward the point at which M2 most closely approaches M1. Now that concept might be a little bit difficult for the ellipse, but if you put in some time thinking about it, you'll see that this vector has to be along the major axis, and it's got to be pointed toward what's called periapsis, which is the point at which the orbiting body most closely approaches that focus, right there, the thing that it's orbiting. Now the case for the circular orbit, it's much simpler. Actually what I could do is attempt to draw in both of these vectors at some arbitrary point in the orbit. Let's say right there. What does mu times r hat look like? That's going to be some vector pointing in that direction. Mu times r hat. Now, what does h times r dot look like? Well, that's also going to be in the same direction. So h times r dot might look something like this. So again, I have a sum or a difference of these two vectors. So what that tells us is that the constant vector must be located somewhere on that line. So that's all we know about the Laplace vector for the circular orbit right there. But let me cook up the same argument for another location on the orbit, let's say right there. Let's assume that this thing is going that way, it's orbiting that way, although it doesn't matter. Again, let's draw in mu times r hat. Now that's going to have to look something like this, mu times r hat. And h times r dot is also going to be in that same direction. So we cook up the same argument and we conclude that the vector must also be along this line too. But the only way that's possible is that the vector is actually the zero vector, because that's where the intersection is. So we see that for the circular orbit, this conserved vector is simply the zero vector. Also notice that the fact that the Laplace vector turned out to be zero nicely corresponds to the fact that the eccentricity for a circular orbit is zero. Now, another thing we can do is remember that we define that dimensionless number e as the magnitude of the Laplace vector, which I called c, divided by mu. I could rearrange this and say that c is equal to mu times e. But this is the magnitude of c. What I can do is say that c is equal to mu, where mu is a scalar, times a dimensionless vector called the eccentricity vector, just converting this into a vector equation. Now I can go over here, take this vector, go over here. Instead of saying that this right-hand side is equal to the vector c, I could say it's equal to mu times the eccentricity vector is equal to h r dot minus mu r hat. I can divide both sides by mu and say that the eccentricity vector is equal to 1 over mu h r dot minus r hat. Just doing a little rearranging here. This is just a scalar multiple of the Laplace vector, of course. The important concept is that this is a conserved vector of motion. You can think of as M2 orbits around M1 in its trajectory, there's a little conserved vector attached to it. So I think that'll wrap it up for this video. As I said for the previous video, this is a bit more difficult than some of the other videos I've done, so feel free to leave any questions you might have in the comment section. And as always, if you enjoyed the content, subscribe to my channel, leave your angry comments in the comment section below, and I thank you for watching.